So, here's another method to do integration, which is called partial fractions. Now, partial fractions is not only an integration method, it's also a method to write rational functions in a more simple form. So here, for example, we have an example 1 over x squared minus 16, which you can write as an eighth times 1 over x minus 4 minus 1 over x plus 4. And so these two terms, 1 over x minus 4 and 1 over x plus 4, they are considered to be easier to integrate than the previous 1 over x squared minus 16. Let me convince you that this equation is correct. So let's just do a quick common denominator thing. We keep the 1/8, we do the common denominator. So we get x plus 4 and then minus x minus 4, and the common denominator is x minus 4 times x plus 4. Okay, and then we keep the 8th, and on top we have x minus x, which cancels, and we have 4 plus 4, which gives an 8. Okay, and in the bottom we have a quadratic formula, so we get x squared minus 16. And then the 8 cancels, and indeed we have 1 divided by x squared minus 16. As I say, I want to use it for integration, so let's see how we can use it for integration. So solve the integral 1 divided by x squared minus 16. Same function as before. And of course I use a formula I just derived, otherwise I wouldn't derive it. So then we have 1/8 x minus 4 minus 1 over x plus 4. Okay, so I just replaced the rational function inside the integral with a simpler function, because this I can integrate. So this is now 1/8, and if I integrate 1 over x minus 4, I just get ln of x minus 4 absolute value. And if I integrate the other one, 1 over x plus 4, I also get a log. Of course, I need to carry the minus sign, so then we have log of absolute value x plus 4, like this. And of course, now we did the antiderivative, so we add a constant c. So you see, the factorization of this function into that sum made it actually possible to integrate. And that's all. That's the secret of partial fractions. So let's try to write this up as a general principle. And here we go. So now we look at the rational function p of x divided by q of x, and we assume that the degree of p is less than the degree of q. So for example, right here, this f, we have the degree in the numerator is 2 and the degree in the denominator is 3. So this would be the case, what we are looking for. Degree in the numerator is less. So then we take this denominator and we write it as a product of distinct linear factors. For example, here, you can factor out an x squared in the first two terms. Let's do that. So this is x squared, and then we keep an x plus 3. And in the other term, we factor out a minus 1, and then we also keep an x plus 3. This is an x squared minus 1 times x plus 3, yoo-hoo, because x squared minus 1 I can also write as linear factors x plus 1 times x minus 1 times x plus 3. Okay, and this is what I wrote here in a different order, but that doesn't matter. This is the factorization of the polynomial q in linear factors. So we call these guys here the linear factors. And that's what we need for the partial fraction method. So then if we have the linear factors, so here they are again, there and there and there, we want to write the whole thing as a divided by x minus 1 using the first factor, plus b divided by x plus 1 using the second linear factor, and then plus c divided by x plus 3 using the third one. Okay, and then of course if you have more factors, then you use more of these terms. And now it is on us to find the a's and the b's and the c's. So let's do that here. So we're going to use it for evaluation of an integral. So what I do first I look at the denominator and I write it as linear factors. And then I take the whole rational function, p divided by q, and write it as a sum of partial fractions. So that's the second step. I do 4x squared plus 14x minus 2 divided by x cubed plus 3x squared minus x minus 3. I want to write this to be a divided by the first factor, x minus 1, plus b divided by the second, x plus 1, and then plus c, and guess what? The third one. All right. So we need to find a, b, and c. And this is easiest done by multiplying with the product of all these linear factors. So I multiply by x minus 1 and by x plus 1 and by x plus 3 all at the same time. Can we do that? Well, let's try. So this product I know is exactly the denominator. So which means if I multiply the equation by it, it will be cancelled on the left-hand side. So on the left-hand side, we just keep 4x squared plus 14x minus 2. And then the product cancels the denominator. Done. Okay, now the a term. The a term has a factor x minus 1, which is also a factor I'm multiplying with. So they cancel. But then the factor x plus 1, x plus 3, these stay. So we get a times x plus 1 times x plus 3. Okay. And then for the b, we have the factor x plus 1, which cancels. And the other two remain. So then we have b times x minus 1 times x plus 3. Yeah, and then guess what? For the last one, for the c term, the x plus 3 cancels and the others remain. X minus 1 remains. X plus 1 remains. Hey, that was not so bad. So now we got an equation which has no more fractions. It is just a bunch of polynomials. But we still need to find a, b, and c. And there are two methods to do this. So here I write down the equation again. And the first method is more or less like a quick and dirty method, which I like to show first. And I just call this Talos method. We are just subbing in the numbers which make those terms equal to 0. Okay, so I say substitute those terms which make the linear factors equal to 0, which means I substitute x as 1. Okay, then the x minus 1 term is 0. I sub x as minus 1, because then the x plus 1 term is 0. And I sub x is minus 3, because the x plus 3 term would be 0 at that point. Okay, let's do this. So I sub x is equal to 1. On the left-hand side then, if I sub in 1, I get 4 plus 14 minus 2 equals, and then for the a, I sub in x is 1, so a times 2 times 4. And now the b term. If I sub in x is 1 here, I get 0. Haha! And if I sub in x is 1 here, I get 0 too. So I just get the a term, which gives me then 16 is equal to 8a. And then, ta-da, we can find a is equal to 2. Beautiful. X minus 1. So then we sub in x is equal to minus 1. We start over. We sub in x is minus 1. On the left, we get 4. And then we get a minus 14 and a minus 2 equals. And now in the a term, the first factor x plus 1 is 0 if x is minus 1. Hey, that's gone. And which else? The c factor goes as well. So we only keep the b term. For x is minus 1, so then this is a minus 2. And the other factor is a plus 2. So then we have minus 12 is minus 4 times b. So we get b is equal to 3. And then the last one, if x is minus 3, so now we can do this rather quick. So we sub it onto the left. We get 9 times 4, which is 36. And then we get minus 14 times 3, which is 42. And then we have a minus 2 here. And then the a term vanishes. The b term vanishes. Only need to worry about the c term. C. and then subbing in -3, so we get a -4 there, and in the back we get a -2. We get -8 equals 8c, so c is -1. Oh, fantastico! So we found the a's, the b's, and the c's. Going back to the partial fractions with our ABCs, we get this. Wait, this. So then the whole rational function, 4x squared plus 14x minus 2 divided by x cubed plus 3x squared minus x minus 3, can be written in this partial fractions, but now we know the a's, b's, and c's. So we have then 2 divided by x minus 1 plus 3 divided by x plus 1 minus 1 divided by x plus 3. Oh, this is rather cool. So that gets a smiley face. Integrating the left side must be very hard, but integrating the right, we get a bunch of logarithms, so that seems to be actually manageable. Yoo-hoo! Before I do this, though, let me talk about the second method. We call the second method Talos Method. You multiply everything out, you get a polynomial equation, and then you'd be a math whiz and solve them. So I will show this then for those who are interested in another video. Okay, so now we go to the integration. This is then rather easy. So we have 2 divided by x minus 1 plus 3 divided by x plus 1 minus 1 divided by x plus 3 all dx. So we do our loggy thing, 2 ln log of absolute value x minus 1 plus 3 log of absolute value x plus 1 minus log of x plus 3. And guess what? I always have a constant in my pocket. If I need it, I take it out. So, plus the constant. There we go. Okay, so the left side seems to be rather complicated. But if we get these partial fractions done correctly, we can actually integrate these functions. Let's summarize. The method is for rational functions, where in particular the degree of p is less than the degree of q, and then we factor q in a product of distinct linear factors. Right, and these factors in the previous example were x minus 1, x plus 1, and x plus 3. We write a partial fraction decomposition using the linear factors, and then we solve for the unknowns a, b, and c. That's the hard part. If we have the a, b, and c, then comes the easy part, which is just integrating with a bunch of logarithms. So that should be no problem. Ooh, oh, oh, ooh, oh, oh, oh God, I think Tolo is in pain. I better check on him. Tolo, what happened? Oh, you poor guy.